Welcome to the Fluid Structure Interaction and Solid Mechanics session of the 16th OpenFOAM Workshop. I am Željko Tuković, and I'll be chairing this session. There will be 4 talks, and every speaker will have 10 minutes for their presentation, followed by 5 minutes for questions and answers. First presentation is by Mr. Gyantse Zhang from Dalian University of Technology. Mr. Zhang will talk about performance assessment of a floating platform surrounded by elastic ice plates. Mr. Zhang, please share your screen.
Can you see the PowerPoint? Okay. Hello, everyone. My name is Qianze Zhuang. It's my great honor to attend this workshop. Today, the title of my talk is Performance Assessment of a Floating Platform Surrounded by Exact Ice Plates. And the talk will be divided into 4 parts: background, numerical methods, results and discussion, and the last one, conclusions. The oil and gas resources are abundant in the Arctic in recent years. With global warming and the melting of polar ice coverages, the Arctic marginal ice zone has generally expanded, particularly in the summer. This is therefore more accessible to carry out oil and gas in the region. However, as shown in the picture, we can see different from the open water. Floating platforms are often surrounded by large areas of floating ice. When the wave progresses from the outside to the platform, the extent of ice flow will greatly change the wave impact force on the platform. Waves will reflect multiple times in the gap between the ice flow and the platform. Therefore, for ensure the safety of platform, it's necessary to access the hydrodynamic lathes combined with the sea ice efforts. Until now, there are little research on wave-ice structural interactions. Meanwhile, studies on interaction between waves and ice have made a considerable progress. The majority of previous work relies on the following 4 methods: analysis, experiment, numerical simulation, and observation. The mathematical methods usually include 3 or 2D linear flow, potential flows through, and linear elastic through. In terms of experiments, nearly studied the interaction between thin ice with different mechanical performance and different incident waves. He discussed the wave energy in this process by analyzing the reflection coefficients and translational coefficients. It should be noted that PP or PVC is used to replace the floating ice. For the last several years, numerical methods has been divided greatly, including the FVM methods or SPH methods and the BEM methods and so on. In many numerical studies, floating ice is assumed to be a rigid body. As for observation, in last century, Square measured the wave attention date in the major ice occurring in the Green Sea and found that the attenuation coefficients of wave progression energy increased with the decrease of wave pressure. research on the interaction between a structure and ice flow is also ongoing. However, the influence of waves was ignored, and also the damage of ice load to the stream is considered. At present, for the interaction between wave, ice, and the structure, most people use the analysis methods beside on these methods. For example, Li solved the problem of wave interaction with a 2D shape structure in an ice lake. In such a context, the certain research work, especially 2D numerical structure ice wave interaction models beside on OpenFOAM. Now I will introduce the numerical methods in this work. The two dimension incompressible flow mode is used to simulate the flow fields, and the generator increment is the NS increment. In the solid, I use the dynamical excess and the interaction between the ice and the waves is relaxed by using a two-way fluid structure interaction with the structuring flow of this method is shown in this figure. This is the model step of our paper. The length of the numerical field is 9.45 meters, and the height is this. And the length of the wave generation area and the wave absorption area is long enough under each working condition. The ice ledger is 1.35, and its material parameters refer to the actual sea date. The mesh adjustment around the ice flow is shown in the picture in the lower right corner. The fluid mesh is dense enough so that the wave doesn't significantly, and the solid mesh can ensure the deformation of the ice to be consistent in the reality. This is the case step. We consider 4 wave legends, which are 2 times 2.5 times 3 times and 3.5 times the legends of the platform. And we also consider 2 gap legends, which is 1 point and half point, half times of the legends of the platform. Therefore, there are 3 kinds of ratio of wave legends to gap lengths in this work. In the research section, firstly, we get the average of the peak values of the wave impact force at 4 wave lengths when there is no ice flow, named FP1 to FP4. Then we need to deal with the conditions when there are floating ice. Here is an example. We can get the wave impact force carrier of the platform. Then we choose a stable temperature of 20 to 30 as the research object, and then cancel DC offset. We divided the view of the cursor in the upper left corner by FP2, which is the origin of the peak value of wave impact force when there is no ice flow. Next, we also take the average peak view of the new curve. Therefore, in this case, the F max means the average of the peak views is equal to 1.39. Repeat the above steps, we can get the F max in different radius of view length to gap length, as shown in the picture in the lower left corner. Look at the left picture. We can find that the ratio of wavelengths to the gap length is equal to 2.5. The F max exceeded 1. This means in this case, the S flow will make the plate structure a greater wave impact force. And the right picture is the FFT resource of the wave impact force. The mean frequency is the frequency of the incident wave. We can find that when the ratio of wavelength to gap length is equal to 2.5, there are more higher order frequency components. This picture shows the trend of the wave force as the wave length increases. We can find that compared with the case without the S, the wave impact force doesn't simply increases with the increases of wavelength when there is an S. Now there are conclusions. Firstly, when there is a gap between S and a floating platform, the S plate can reduce the wave impact force in most cases, but sometimes the wave impact will enhance it. Secondly, the influence of the wave the S flow on the wave impact force is related to the ratio of incident wavelength and gap length. Thirdly, the flash S will change the law of the wave impact force changing with the wavelength. At last, the high frequency components produced by multiple reflection may be one of the reasons for the increase of the wave impact force. This capture of the model is this is all I want to say. Thank you for your attention.
Thank you very much for nice presentation. We have time for a few questions. So first question is related to the solver you were using for solid side. Have you used something different than OpenFOAM, or you were using OpenFOAM for solid?
I use the OpenFOAM, the Foam Extender 4.
And you use solids for foam library, fluid structure?
In fact, I use the Vivo FSI foam.
FSI, old version of the
yes,
library. Okay.
Yes.
So one question is related to buoyancy force. Do you calculate buoyancy force automatically?
In fact, yes.
Okay. And this is a result of calculation, yeah.
Yes.
And
I think I can research more case.
And last question is related to initial condition and boundary condition you use for your simulation. Can you tell us a little bit more about this? What were initial conditions for your calculation?
You see this picture.
Unfortunately, we cannot see your slides anymore. Okay, so I think you can pass through the question queue and try to answer remaining questions. Okay.
Yes.
Okay, so could you please stop sharing your screen now?
Okay, okay.
Thank you very much. And we can go to next presentation. Second presentation is by Dr. Paul Schmidt from Queen's University, Belfast. Mr. Schmidt will talk about Neptune's spaghetti, bending actuator line model or models.
Yeah, thank you for the introduction. I also want to point out my colleague Desmond Robinson, who has been involved in this work. Probably the biggest infrastructure offshore that is being built, so I'm a marine engineer originally, is obviously offshore wind. And I really want to point out just how many slender structures are involved in all these offshore operations. It goes from obviously the turbine, the support structure, but also, for example, jackup vessels. I do quite a lot of work, for example, on tidal turbines. You can see a device here that's a 16 diameter rotor, and that's suspended on a long beam. And that turbine was actually installed for 8 years just behind my house here. There are other tidal turbines, of course, again, cross-flow turbines, very complex fluid dynamics, very, very large structures made up of tinier structures. We have underwater robots that are mostly built out of cages and then supported by tethers and chains and similar structures. Very exciting if you're into sailing. There is now, well, America's Cup maybe the most famous. There are surfboards that are foiling. There have been foiling ships around for quite a while, but it's really picking up now. They are foiling bicycles or water cycles or whatever you want to call them. Loads of simulations, and last but not least, also fish cages. Interestingly, it's quite a challenging topic to assess those. And if you look at typical technical profiles, for example, like just a simple NACA profile, the typical benchmark test cases in relevant Reynolds numbers, they tend to suggest that you need about 200,000, 250,000 cells to really resolve them accurately. And that is only for 2D slice. And you can imagine, for most of the structures I showed you before, if you really wanted to resolve these slender structures with that type of resolution, you're talking hundreds of millions of cells, which it can be done, but very often it's not really practical in industrial applications. And you always need to keep in mind, if you're doing offshore work, of course, we're talking about the need to resolve length scales that are somewhere on the length of waves or the water depth, which is hundreds of meters. And the boundary layers then are so small that is really the major challenge. And one method, I'm not saying it is a one-size-fits-all approach or so, but one method that we found very useful is, of course, the actuator line method, where you actually do not resolve the geometrical feature in detail, but you take the forces from a database. Most of these technical profiles are very well defined from experiments, and then you just apply the forces acting on them onto the fluid, so you get the weight correctly and so on. And the pre-processing becomes a lot easier because you don't have to do, or you don't have to represent your structure in the background mesh, right? And that really makes it sometimes much faster. And especially for wind or tidal turbine wake studies, it has been used quite a lot because you can focus all your mesh resolution into the wake coming off. So it is horses for courses, but when you look at such a method, the way it really works, the data structure is you define a line and then you have sections, and at certain points you evaluate the section force and you get the fluid forces on your structure. And as an engineer, it reminds me immediately from a beam element analysis, as probably most of us have done at university or so. And because the actuator line method in itself is very efficient, I found many applications where it would be really useful for me to also take the deformation and the forces in the structure into account. And that's why I set out to enhance it a little bit and add an FEA tool below it. And then the idea is that I get deformations and I can put in structural boundary conditions and simulate that. And this is very much ongoing work. So I took the actuator line model that is quite well known, turbines foam, from Pete Bachon. There's a publication from 2018. And I interfaced it with an FEA tool. And after some consideration, I implemented a pure frame analysis or beam element toolbox. It's currently steady state. But we are already planning to enhance it for transient simulations. Also, I picked the Armadillo library. So I kind of inherited the FEA tool, and it was originally written in MATLAB Octave. And I used this Armadillo library to rewrite it. It's not that much code. So the whole library is a self-contained small unit. And yeah, what can I do by now? Well, you can have a wing, so that would be an actuator line model. The original line is the white line, and you can see you have negative pressure on top and higher pressure below, and the whole thing creates the forces that you can see on top here as the red arrows. And now we can also get the deformation. It's exaggerated here, but the beam is deflected upwards. And if you do the analytical calculation, you can also see that results luckily match. So all that seems to work. And a typical beam element can also take, of course, torsion. It's interesting for some of our cases. So that is now a supporting beam in flow direction. So the fluid forces are 0. And then you have, again, a wing structure pointing sideways, and the lift force or the resulting forces create a torsion. So that's the deformation you can see here. And the original position was, again, the white line, and you can see the analytical solution would match with the yellow line up here, and we are spot on. So that makes us quite happy. So that's some simple validation cases. Of course, the practical applications, and I'm referring now to the start of my presentation, what we are actually working on is, for example, tidal turbines. This could be a turbine. It is still very early stages, but yeah, you get pressure at the front. So higher pressure at the front, you get the flow swirling around a turbine. That is all the standard actuator line method. And what we can now also evaluate is the deformation of the blade during the rotation. Another topic we are interested in, and this example also highlights two-phase flow applications. So that's something we are progressing the validation. This is the famous Wrigley hull, of course, and you get a wave pattern around it. And as I said in the introduction, if you want to go really fast, you need to put little foils below it, lift it out of the water, get rid of your wave resistance, and blast along. So this is something we are looking at too. And last but not least, slightly obscure, I can't give you too more details. But if you had flexible structures put vertically into a tank and you have a wave passing across it, you would then get the deformation. And it's quite of interest to us how the wave is damped depending on the structure parameters, so the small scale deformation of these vertically implemented structures, whatever they are. So that was a quick overview. As I said, it is work in progress. I'm now working on the transient FEA code and coupling that together. There's quite a lot of debugging to do and profiling of the entire code. So turbines foam itself was still under heavy development and is work in progress. And then I'm really looking at application and validations to offshore problems. A couple of them I showed you just now. One topic that would require a bit on the FEA side is also including bend twist coupling for turbines. So it's a quite popular load shedding mechanism by now that when the turbine is loaded, it decreases the angle of attack by twisting, and that is a structural property. So that is also something we are looking at. Thank you very much.
Thank you very much for a nice presentation. We have enough time for a few questions. One question is related to, I'm not sure which case, but a question is related to mesh generation.
Yeah.
Did you use Snappy?
For which one?
I don't know. you showed many cases, so.
Well, the key thing is, yes, I do use Snappy, but with these actuator line models, the meshing is that easy because you really define your structure just as a position of nodes and then the sectional parameters. So the meshing is that easy. So maybe it was confusing now to see the wiggly hull or so. But once it's out of the water, it doesn't matter too much unless you go with really crazy velocities, I suppose.
Yes. So next question is related to vortex formation. Just wondering, have you considered the vortex formation near the turbine blade?
I have not yet, but there are many papers about the wake structure. So it's really popular now, for example, for tidal turbine wakes. And it obviously doesn't work well very close to the blade because you don't really have the blade, right? So the forces are imposed in a certain area. It is a very coarse model. You also have some semi-empirical corrections to take a 3D structure into account. But there are many studies that have been well validated to resolving the full wake and the vortices coming up with the tip vortex.
So can we say that this is kind of a one-way coupling model where you get correct force, but the influence of the blade on the flow is not so accurate, yeah? And
I'm not sure I agree because you do take into account the change in inflow, right? Because you are influencing the flow field and then you correct your forces depending on the inflow. But there are open questions, for example, if you use it for hydrofoil simulation, your lift forces change when you get into surface proximity. And I'm not too sure. There are lots of analytical models which we could implement for correction, but we need to look very carefully what is actually required.
But you showed the turbine model with 3 blades. So there is one, I would say, one beam which is aligned with the blade axis or blade midline, and you have many transversal.
No, that's just for post-processing. Sorry, that might be confusing. So it is really just one line. This is just an added-on visualization, so I can check the. It visualizes the actual chord direction that is used in the simulation. It is just one actuator line that goes along.
Okay, one last question. May I ask the accuracy of this method, and does it need any predefined coefficient prior to simulation?
Yes, a lot. It completely depends on the good characterization of your two-dimensional profiles, right? And there are people who kind of calibrate it for some sections, but I think it is really only useful if you have standard sections. So all the NACA profiles are fairly well defined. Round sections, of course, are also well defined to get your drag forces on the round beams. And that covers quite a lot of technical structures. It is not the right tool to design a turbine blade in detail. Definitely not.
Maybe one more question. Did you consider to use adaptive or overset mesh? So I suppose overset mesh is not your option, but adaptive, I suppose, would help you, yeah? So your mesh should be refined along the actuator line, I suppose.
Yes. Yeah? Yes, but the mesh refinement required around the actuator line is still a lot less than what you would need to resolve a full 3D geometry with the boundary layer, right? So that's an order of magnitude difference. So my feeling is it is much better in 99% of the applications to just have a slice refined where your actuator line is moving, and then probably you want to if you want to resolve the wake, you need a very high mesh resolution in the wake anyway.
Yeah.
But
okay, I think this is
thanks.
enough. You can check the question queue if you want to answer remaining questions.
Yeah, please get in touch.
Thank you very much, and please stop sharing the screen now. If you can stop sharing the screen. Yeah.
It doesn't offer me to release my screen.
Yeah, he has stopped sharing. I can share the next presentation.
Okay, so
Right.
next presentation is by Hao Hu from Shanghai Yao Tong University. Mr. Hu will talk about numerical study of vortex-induced vibration suppression of a flexible tangent riser with span-wise grooves.
Hello everyone, my presentation topic is numerical study on vortex-induced vibration suppression of a flexible tangent rise with span-wise grooves. The presentation includes 4 parts: background, numerical method, results and discussion, the conclusion. First, I introduced the motivation of paper. The vortex-induced vibration is well recognized when the rise is exposed to current. The multi-mode vibrations and mode transitions of the rise structure caused by vortex-induced vibration are the most important source of fatigue damage. Then I will turn to the numerical method. First, reference equations are adopted to compute the follow field, and the continuity and momentum equations have following form. The Reynolds stress is computed by SAT omega turbulence mode. The structure governing equations are solved by finite element method, and the rise is consumed to be a Euler-Bruni bending beam with pretension. The mass spring dynamic equations in the x and y directions is here. In this slide, we compare the current numerical solution structure for follow field. The first 3-dimensional simulation method, considering the larger aspect rate of the rise. 3-dimensional simulation method for anti-follow field requires huge cost of computational resource and time. The second 2-dimensional strip method. The 3-dimensional follow dominant is replaced by a series of 2-dimensional follow strips in this actual direction. Although this method can save the computational resource and time, strip theory neglects the actual correlation in this 3-dimensional follow field. In order to predict the hydrodynamic force around the rise with complex cross-section structure, Bohr put forward the generalized 6-strip mode that the 3-dimensional fluid strip was instead of 2-dimensional fluid strip. Based on the 6-strip mode, the VIV-3D form SJTO slope is derived based on the OpenFOAM. The strict 6-strip mode. The boundary points are uniform distributed on the CDM surface in each 6 strip. and the boundary points at the same actual position will be given the same vibration displaced in both x and y direction from the cylinder through the cubic spring interpolation method. The computation method will then be updated on the basis of the motions of the boundary points. Use the dynamic grid technique in OpenFOAM at each time step. This slide shows the schematic diagram of computational mass and the 10 equidistant two-dimensional force strips with the same initial mass along the span of the rise. The cell number of each strip is 14.6 millions. The size of the computational domain is here. D is the cylinder diameter, and L is the cylinder length. The structure and the follow strips boundary conditions are shown here. This is the main parameters of the rise. Then we introduced the motion results. This slide shows the different span-wise groove geometries. Figures plot the model weights of the cross-flow displacements based on model decompression method. It can be seen that the dominant cross-flow vibration mode is both fixed at first vibration mode for the three cases. Meanwhile, the amplitudes of first and second vibration modes in case 3 are slightly smaller than that in case 1 and case 2. Figures plot the model weights of inline displacements based on model decompression method. By the comparison of the amplitudes of different vibration modes, the results indicate that the second vibration mode is the domination inline vibration mode in case 1 and case 2. As the groove dip increases to 0.16 D, the dominant inline vibration mode rises to third vibration mode. The dimensionless rows mean square of the cross-flow displacements along the rise span are shown in this slide. At the variation of the groove dips, the cross-flow vibration mode shape is basically consistent, and the location for the maximum amplitude of the vibration is different along the span of the rise in the three cases. The figures show that the amplitude of cross-flow vibration is placed in case 3 with a comparison of case 1 and case 2. The dimensionless rows mean square of inline displacements along the rise span are shown in this slide. The amplitude of inline vibration is enhanced with the groove dip increasing to 0.12 D. Due to the elimination of rise ignition, the rise of mode brings the decrease of amplitude of inline vibration in case 3. The voltage shading for different times are shown in this slide, and we can see different vortex shading phenomena at different strips for the same rise, and the structure vortex shading phenomenon is more obvious in case 1, and we know the amplitude of vortex vibration is the biggest in case 1, so it is corresponding. Finally, we make some conclusions. The dominant inline vibration modes are affected by groove dips. The amplitudes of a cross-flow vibration mode can be expressed with the increment of groove dips. The different VIV response of the different groove dips result from the interference effects of the vortex shading. That's all. Thank you.
Thank you very much for the presentation. Since this is a pre-recorded presentation, we do not have opportunity to ask questions, so we can continue with the next presentation. So our fourth presentation is by Mr. Andrew Whelan from University College Dublin. Mr. Whelan will talk about implementation of damage mechanics and fracture models in OpenFOAM.
Second. Okay, so my presentation is going to be on the finite volume implementation of damage mechanics and fracture models. So in this presentation, I'm going to just discuss the implementation of two damage models and the phase field fracture model. So just to give a quick example of what these models can do, here we have a flat tensile specimen. And then as it's pulled apart, we can see that the damage model predicts that the damage will occur center the specimen. Here we just have a flat square plate with a notch in the middle of it. And we can see that the phase field model predicts that as this square plate is pulled apart from both sides, a crack quickly spreads across from the edge of the notch to the edge of the plate. So to my knowledge, these models have not before been implemented in OpenFOAM or using the finite volume method, more generally speaking. This work therefore serves to extend the capability of OpenFOAM software to simulate these damage mechanics and fracture processes. So the first model I'm going to discuss is the Lemaitre damage model. So in this model, a representative volume element is isolated from a damaged body, and a damage variable D is introduced. What this damage variable basically represents is, if we look at a plane on this representative volume element, it's equal to the original area of this plane minus the area after cracks and cavities have taken place over the original area. So D will be equal to 1 in the fully damaged state, and D will be equal to 0 in the undamaged state. This variable is coupled with the elastic plastic model through the concept of the effective stress. So the effective stress is just equal to the stress that would exist if there was no damage taking place over 1 minus D. So the constituent equation for the damage variable D is derived from thermodynamic arguments and is given by as follows, where Y here is the energy release rate associated with the damage process, R and S are just material constants, and gamma is the plastic strain rate. So just to verify the implementation of this case, it was verified on an axisymmetric notch bar case. So this notch bar is axisymmetric about its axis and symmetric about its middle plane. And therefore only a slice at the top needs to be modeled, as you can see here at the mesh, and a fixed displacement is applied on its top face. So the resulting damage and equivalent plastic strain values for the cell at the center of the specimen is then compared with the results from Bouchard et al. And we can see here when we compare the results, so we compare the equivalent plastic strain and damage values at different displacement values, and you can see that the results from my implementation of those from Bouchard et al. Align pretty well. So another thing to talk about with these damage models is the phenomenon of mesh dependency. So essentially one of the major drawbacks to damage models is that they lead to mesh size and orientation dependent results. So the results can your results can change depending on how your mesh looks. So we can see here an example of this. So this is just a force versus displacement curve for the axisymmetric notch bar case from previously. And we can see here that as we refine the mesh further, increase the number of cells, the damage localizes quicker, and it gives you different predictions depending on how refined the mesh is. So the way we avoid this is by adopting non-local or gradient models. So in this non-local gradient model, a non-local damage variable D hat is introduced. This is implicitly related to the constitutive damage variable D through a diffusion differential equation as follows. And that's just what that equation looks like when implemented in OpenFOAM. So we can see here we have the force versus displacement curve from the axisymmetric notch bar case. And you can see here that as we increase the number of cells, it converges on just one solution. So we have a consistent solution across different cell values. So our problem with mesh dependency is reduced, mitigated, or mitigated at least. So the next model I'm just going to discuss is the GTN damage model. So this model is one of the canonical models used in characterizing the degradation of ductile material. It takes a micromechanical approach to describing the material behavior by positing the existence of micro voids in the material. So the degradation of material, therefore, then occurs as a result of the nucleation of these voids. They then grow and they then coalesce to form more larger scale cracks and cavities. The void fraction of a given volume is denoted by the porosity variable F. So our standard yield, so the way that this is coupled then with our elastoplastic model, so our standard von Mises yield equation will be given as follows, which is equal to the equivalent von Mises stress minus the yield stress. The porosity variable F is then coupled with the elastoplastic model by introducing a new yield equation, as shown, where here P is the pressure and Q1 and Q2 are material constants. So this model, so the implementation of this model is then verified by conducting a one element uniaxial tension test and comparing the results of this from Mansouri et al. So we can see here just a stress versus strain graph for the uniaxial tension test. And we can see here how the results implemented locally in OpenFOAM matches up well with the ones from Mansouri et al. So now I'm going to discuss the phase field fracture model. So in this method, sharp cracks are regularized over a continuum, leading to a system of partial differential equations that are relatively simple to implement in finite volume solvers. So you can see on the graph on the left, or the image on the left, in A, we have just the sharp crack, and in B, the sharp crack has been diffused over a larger surface. So in this model, the sharp crack can be described by the variable D. For the unbroken state, D is equal to 0, and then for the fully broken state, D will be equal to 1. So the sharp crack topology of the material surface is replaced by the following equation to give us our diffusive crack surface. So it's a phase field equation, I'd say. And here L is a length scale parameter. So this length scale parameter does is it governs how sort of spread out our crack will be over the surface. So we can see in the image on the right that as we go from A to D, L becomes smaller and the crack is less and less spread out over the surface. So our governing partial differential equation for this model, so from variational arguments and balance law equations, the following partial differential equation is derived, which governs the evolution of the crack variable B. So that's our partial differential equation that we need to resolve our model. So in this model, GC is the critical fracture energy per unit area, and WP is the elastoplastic energy contributions. And then again, we see here what this equation looks like when implemented in OpenFOAM. So in order to verify the implementation of this model, a simulation of a flat notch bar being pulled from either side, as in Bourdain et al. Is conducted. And here we can see a stress strain model, a graph of the stress strain distribution for this case as it's pulled apart. And we can see that the results that we get from the local implementation of this model is equivalent to the ones obtained from Bourdain et al. And that's just for the references for this presentation. And that's it. So I'm happy to answer any questions people may have.
Thank you very much for a nice presentation. So I can ask something related to phase field method. So what are actually boundary conditions for this phase field at the outer boundary of the body?
Just a zero gradient one boundary is the one they usually use. There is a little bit of debate in the literature, but at the moment they pretty much just say just use a zero gradient one.
So and then I didn't notice you have some source term in the region where crack will occur, or
sorry,
what happens in the crack region actually with the phase field? Do you have some source term there, or?
So the source term is the I suppose elastoplastic energy contribution. So that's what governs how the crack spreads, if you get me.
Mm-hmm, mm-hmm.
And
at the moment when this fracture variable, phase field variable is equal to 1, you will have zero stress state there or something like that.
Yeah, it's sort of the variable d sort of asymptotes towards being 1, and at that point, at that point you effectively have zero stress contribution at that region.
Yeah. So can you with that model predict stress concentration in the part where you actually at the tip of the crack?
Yeah, well, your standard elastoplastic model will give you that stress concentration, and then that obviously feeds into the phase field model, leading to the development of the crack itself.
Okay, yeah. Okay, we have one question from the audience. Apart from the non-local gradient damage formulation, is there any other approach to mitigate the numerical dispersion, mesh size, and orientation effects?
They're all pretty similar. The other one people use is a sort of integration model. So you effectively sort of integrate the damage in kind of almost every region, and then you sort of resolve those integrations. Like so that's the other way of doing it, but it's conceptually very similar to the gradient model.
And another one, great work. I was wondering which phase field equation was solved for the present case. Also, how the parameter I affects the result. I don't know.
Is this the parameter? I think L isn't the character.
Maybe L. Yeah.
Yeah. Well, L. So ideally, L is the smaller L is. I guess it's a trade-off. You can use a finer and finer mesh, and therefore use a smaller value of L, and that'll give you, I suppose, more accurate results. Obviously, the finer the mesh, the more accurate it's going to be. But obviously, that's more computational time. But usually, like you can get still very accurate results with still an L in the region of like millimeters. That comes to mention.
Okay, I think this is all. Thank you very much for your presentation and for answers also.
Thank you.
Okay. With this, we conclude this session. I would like to thank all speakers and, of course, audience for attendance. Thank you very much and goodbye.